Welcome back. This is tutorial 8, modeling volatility. So before we start, as usual, a little bit of admin. Report 1 is due next week. It's on Friday next week, so you still have a little bit more than a week. But yeah, just a little warning about it. If you guys need any help, please join our consultations or the end of our tutorials, so we can give you a hand, particularly with the code, if you're finding an error or something. But other than that, that is it for today. So please save these files today. We'll have just one data set. It's the Commonwealth Bank stock shares. It's this CSV here, and probably you want to save the PDF with the questions too. And then I will ask you to copy this code from CodeShare and paste in a new script so you can follow everything. Make sure you save this script in the same folder as you have saved your CWB CSV file. So I'll just click there, copy everything. So I select everything, copy, and then I'll paste in my R. I'll create a new script and paste the whole thing. It's all there. Let me also, I will copy this link just to have it for the people on Zoom. Whoop. Let me just do it like that. Copy link, I'll put it here in the chat so you guys can just click there, don't need to type. So let's go. All right. So today we're talking modeling volatility, and we will be talking about this arch and gauge models or errors. And at the end of the tutorial, we should be able to detect the presence of heteroscedasticity using the Bruch-Pagan test, construct an adequate set of models with possible gauge errors, and use R to estimate volatilities based on these models with gauge errors. Okay. So to start with, first question problem. Consider the daily share prices of the Commonwealth Bank for the period of the 5th of September 1996 until the 30th of August 2006, right? So we will have this daily observations, 2,600 observations, and let YT denote the process of share prices. So this little YT in between curly brackets, it's our stochastic process, right? So you have here, if you open on Excel, you will see these things here. Try not to save, because when you save in Excel, it tends to change the format of the date. But if you want to open, this is what you see. And we'll start by using these 3 libraries. So let's go back to R. I hope you guys, let me know if you can't see the R, but you're supposed to see this here. Right, so I pasted all the code there. Now I will save this script in the same folder as I have the other ones. So this will be live, and you can run. First, we'll just house cleaning. We'll clean everything we have, but it's the first time we were using the library R univariate gauge, so RuGauge. So probably you have to run install packages for this one. If you already have it, you can go straight to the libraries. And if you haven't, run the install. When you finish, you can already do like a comment, because you probably don't want to keep installing every time you run this code, right? So let's go. This, since I have already saved in the right folder, I can use this little line that I usually have to set our working directory to our folder, to the same folder, so we know where the CWB file is. If it doesn't work, you can also put set working directory and choose which folder you put your CWB, or you can to source file location. It will set this folder as the same where you have this file. So let's load it. My data. You read the link, same thing as we always do. They have a header, it's true, and separator, it's going to be comma. You will see everything there. If you open my data, it's a little bit pretty much the same as we had before in a picture. And we're going to store, columns into new variables. So I think for your report, it will be interesting to have a look at how we're doing storing dates. I think your report, it has in a certain format for a different thing like quarters, but have a look at what we're doing here. Our dates are day, then month, and then year, and the year has 4 digits. And they are all separated by slash, like this, I think, for you. So we're doing date receives this information from that is inside of my data, but we're setting the format to be, we're telling them, look, this date where I'm giving you, it's in this format. So you open and close brackets, or quotation marks, but inside percentage M gives the month. Did I say the wrong thing? Let me check it again. Oh, I said the wrong thing. First is month and then it's day. Now I can see here. So percentage month for the month, then a slash because it is separated by slash. Then day, percentage D, both in not capital and in lowercase, and then percentage year is capital because we have 4 digits. If we had 2 digits, we would have just this little y, lowercase. We have a capital Y because it's 4 digits, right? So the original one, I wanted to show, if I print this guy, look how I have everything. But after I run this date, when I print, look at the difference. It separates with a little dash. It doesn't mean the dash itself, it's not the most important thing. Sometimes it will show a Q for quarter, but it means it was able to convert in the right way. So R now understands which date we're talking about because we gave kind of a template of what date we were talking about. Okay, so that's a little bit what's going on there. This is important. You might have to do something like that for your report if you're struggling on having the date and making the date work. So the other ones are the same as we did before. First, we will get just the price. We're taking it from inside of my data and put in Y. And we will use later. But this is the log difference. So I'm taking, so if I print Y, you'll see these values. You'll notice that the price of the stock varies from 10, goes here, it stops printing, but it goes until somewhere around 40, if I'm not mistaken. It goes until somewhere around 40. But then if you take the log of Y, you will see it's a smaller number. It's just between 2.37 and 2.3, and then if you go further down, it will go a little bit further, but it doesn't go to 40. It goes until 3 point something, maybe 4. And then after taking the log, we take the difference of log. So it's pretty much what we're doing there is log of Y minus log of Y, YT minus log of YT minus 1, right? Which is basically we're just calculating the difference, how much it changed in between each observation. So every day in this case. So let's go back to the slides. We read the data. The first question, plot share prices YT and comment on possible features of the data generating process. So we plot it. You see it goes a little bit above 40, as I said. So you can run it here. Goes a little bit above. And you see it's increasing. So if you want to think something. It's pretty good growth in around, I would say a little bit less. In about 10 years, it grew fourfold. This is pretty good. This is not bad, I would say, for Australian stocks. So that's it. I mean, in regards, so it's continuously going up. Probably looks more like a random walk than anything else, right? Maybe a trend here going up, but that's it. Share price is clearly trending upwards. All right. Second part, plot returns. So log of YT minus log of YT minus 1 and comment on the possible features of the data generating process. So once again, we're going to plot, but we will start, in this case, R has one less observation than Y. Why does that happen? When you take the diff, remember, the first one, we don't know. Your first observation, we don't know what to subtract from it. So you don't have that information, right? So it's always one smaller. And you will see that there are 2,605 observations for Y, as we had in my data. But after we take the diff here to calculate R, it's one less, so 2,604. So to plot it, we do this little trick here, date minus 1. So it also subtracts one date, and then you can plot R and type a line and no labels for the X, but returns in the Y labels. So if you plot, this is what we get. So returns usually tend to look more like a stationary process, or like a white noise, if you will. And this is what we can see here. Usually having a look at these log differences or these returns gives you a good idea if the variance is stable, if you have just a single variance everywhere, or if it increases, then it decreases. We can see here for some moments it's pretty low, and some of them, there are quite some large spikes of volatility. So these are some of the features of the returns plot, right? So I'll just click here. As you can see, returns look stable and possibly heteroscedasticity. I think it means heteroscedastic here. So little spikes and etc. Okay. Let's go question 3. At the beginning, it's very repetitive and pretty much things that we have done already. So we can go relatively faster and get into the beginning on what's new. So question 3, we have assuming homoscedasticity, identify an adequate set of ARMA models for RT. So let's go there. This will be the same as we usually do. So ARMA estimation will be, sorry for that. ARMA estimation will be, we start a list, which is going to store our estimations. Then a little matrix here. And this matrix, I see ARMA, will be a matrix 4 by 4. And why is that? So you will see later. But we're running, in our ARMA model, we will be running values from 0 to 3 for AR, for our P, right? And 0 to 3 for MA, for moving average, which is our Q. So 4 models of this and 4 models of that. The combination of both, it's 16. So that's why we have a 4 times 4 here. Number of columns will just be 4 because we will just store P, Q, and AIC in our matrix. So I'll start running. This starts the matrix. It's an empty matrix without column names. Then we're going to give some column names. Now our matrix will store the number of autoregressive logs, AR, the number of moving average logs, Q, and then our AIC score and BIC score. Same thing as we've done before. So it's a 4 inside of a 4. We will have this little I receiving each of the matrix rows. So this little I is the index going in this matrix here, then here, then here, then here, then here. And so it gives some direction there of what's going on. So let's run it. All names, and now this one. With the matrix rows, then the ARMA estimate will receive this ARIMA estimation. This ARIMA is coming from our package forecast, the same as we've been using since now. And we're generating these ARIMA models on our returns, not our price stock shares. So pay attention that we're using R here. And the order is as before, the ARIMA P and Q, right? Sorry, ARMA. And the I, it's always 0, so no differences. We're already using our returns. And then AIC here is just to restore the scores and the model. So now let's have a look at the top 10 AIC, top 10 BIC. For top 10 AIC, you see a few combinations. We didn't generate a lot, so we just have 16. So taking the top 10 already takes almost all the models. And top 10 in BIC, a little bit different. There is, for the BIC, there's one with 3 legs, but I don't think the same guy is here. So for the AIC, so when we run the intersect both of them, look at what we have. We will have just this 3 model, this 7 models here. And after that, let me see. Let me go back to our slides. So you have the code. We're doing the same thing. After that, we're selecting just a few of these models. So we will get from 1 to 3, 1, 2, and 3. The 3 guys here. Then we were getting 6. We will get 6. So we're not considering this ARMA 21. We're not considering this ARMA 03. And we are also not considering this ARMA 12. And we will also, let me see, we will bind it with our BIC model 2. So we're binding it with this ARMA 10. Okay. So that's what we're doing for this adequate set here. So then we will have just a moving average with 1 leg, moving average with 2 legs, autoregressive with 1 leg, autoregressive with 2 legs, and an ARMA 11. So let's run. And then match is just taking the indexes so we can use later, right? Now check the residuals for the specifications in the adequate set. So first, this is number of models. It will take, as you can see, it's just 5 because our adequate set has only these 5 models. And then we're going to check the residuals for each of our models. All of this we've done before, so nothing new. When we're doing this Young box test, we're seeing if we're rejecting this null hypothesis of autocovariance usually in the first 10 legs of the residuals. I think for the 5 models, it's just using 10 legs. Sometimes it will be more, but we're not rejecting any of them. You will see the values here. We can go back to the slides. Look, it's all okay. So we're not rejecting, we're moving forward with all of them. But look how interesting it is. We're not rejecting because we don't have like any autocorrelation that is statistically significant in the residuals, at least up to the 10th leg. There's nothing. So I can move here to the second one and then to the third one. Maybe this a little bit. It's crossing a little bit there, but it's still pretty low. It's minus 0.04, very far from a 1. Also here, nothing. And I think that's it. Is there another one? This one. Okay. But when we're talking about volatility, now we get to something new. Question 4, generate estimated squared residuals for the set of models chosen in question 3. Plot the squared residuals along with autocorrelation functions and interpret your findings. If you watched this week's live lecture, Eric was emphasizing and explaining, going deep of why do we look into the squared values when it comes to volatility and when it comes to variance. If you look at the variance formula, you'll see it's the difference between our observation and the mean that we found, and then we square. So that's a little bit why, but watch the live lecture to have a deeper explanation of why having it squared starts showing you the volatility. So let's go. Look at what we're going to do. I will show you step by step how we're doing in the code. So 4, we will create this little list here, E squared. So E is our error or our residuals, but E2 is the same but squared. So E2 ARMA, it's a list. We started here. Now, for each of our models, we will run I from model 1 until model 5, because in mods, it's a 5. And then the first step we have is to get the squared residuals for that model. So look at what we're going to do. So this guy here, for example, starts at 1. So E2 underline ARMA 1 will receive the residuals. So we're using this function called resid. If you want to have a look at where it is, you can go to help and put resid, extract model residuals. Pretty simple. And then we get the ARMA estimate that we created in the back here, this list of models. And we just look for the, where is it? We look for the adequate index that we also save back in here for the first one, for example. So the first model would be adequate index, the second one, that's what we're looking. But we're not saving just the residuals. We're saving the residuals to the power of 2. So the residuals are squared. And what happens when you square? Residuals usually go around 0, right? At least it's what you expected to go around 0. But now that you square it, all of them are going to be positive. And the larger residuals will be much larger now. You're accentuating a little bit. Then, first, so let me run it so we can have something to look at. And there were 5 models. So you will see 10 plots. And I would like to show you what's going on here. So the first thing is just the title of the plot. This is paste is putting together some strings of characters. So ARMA open, and then we get the P value, like the legs we have for autoregressive leg, the autoregressive legs, and then we have the moving average legs. And then we close the bracket, there's a comma in between, so pretty much we're just writing ARMA 01. Then we're going to plot these arrows squared. So the same date to the -1 plot, ARMA, then type is a line, so we're kind of connecting the dots there. And then YLab is the no labels for X, XLab, no labels for Y would be squared residuals. And main will be paste plot column ARMA 01 for this one specifically. And look what I was explaining. So now everything is positive. While if you plot it without squaring, it will probably go around 0. There will be positive and negative numbers. Now everything is positive. And also, where we had a little bit of variance, now it's even more because we squared. So larger values are much larger than the ones that were smaller, right? So the next step is taking the ACF, and you will see S ACF written here. If you don't know, S is just saying that it's the sample ACF. So don't worry about this. S is the same ACF that we've done before. And we're taking it. You will see the title. We're pasting the same title here, the type of AMA, but we're using SACF column for the AMA. Do you remember that it wasn't statistically significant when we looked here? Now, it seems that it is. Now that we put the error, now that we squared the errors or we squared the residuals, now we can see a little bit of autocorrelation here. And that shows that there's probably some arch or arch lags. This is one way that we identify. So this is the test we're doing. And you will see that it repeats for all the models. The lag 0, as you know, it goes to 1. But you can see that these ones are going pretty high. It's going up to 0.2. Third model. Fourth model. Finally, fifth model. So I have here in the slides, you will see this autocorrelation now that we squared. So squared residuals appear to be strongly autocorrelated, even though autocorrelation in the residual level, so the young box test we did before, appears to be quite low. We interpret this as evidence of conditional heteroscedasticity, possibly being present in our data generating process. All right. So that's it for this one. We're doing this visual and manual check of if there might be some heteroscedasticity in our data generating process. All right. From there, let's go to this one, to question 5. Test if the errors in our set of models contain arch or gotch effects. So before it was a little bit more of a visual test and some instincts to see, as we tend to do with the plots. Now we're going to do a formal test. And first I will print it here, a lot of things, but we're going to do the Bruch-Pagan test. And just as a caveat, like a little bit of Easter egg here, both Bruch and Pagan were UQ students, economics students. They're both first class honors in economics at UQ around end of 60s or 70s. So some time ago, but it's really cool that there is a process that they developed and they're both from UQ. So let's go to A and we can do it step by step. Now this is new. This is not repetitive anymore. Well, squaring wasn't also new, but let's go. Bruch-Pagan test. We're going to create a matrix, and this matrix will have, we're going to analyze up to 10 legs for each of our models. So it's receiving 10 rows times the number of models we have, and we will have 5 columns for it. What are those 5 columns about? We have here in the call names. P is our autoregressive legs. Q is our moving average legs. J would be how many legs are we considering? How many legs are we analyzing? So this is our model. And then this is the test for how many legs we're doing this Bruch-Pagan test, right? And LM statistic that we're calculating, and the p-value related to that LM statistic, right? Look, this might look a little bit more of a calculation. It's something that you can plug and play to your assignment, and feel free if you have some difficulty making it work for you. But pretty much as long as you have your models saved somewhere and you have the number of models, this should work for you in your future assignment. But let's go. So in our 4, let me run the lines, and once again, let's have some visual of what we're doing. I would like to print. This is very large to print. But so I will show you to have an idea first. Bruch-Pagan, we have the models, we have the legs. So for the first model, 0, 1, will be from 1 to 10 legs. Then we have a statistic, and then we have a p-value, right? This is what we're doing. We're generating these numbers. So let's go little by little. First part, e squared I will receive as a vector the model e squared armor I. So this is coming from, I think, a list was the previous type. Now we're transforming it to a vector. It's a vector of residuals, okay? Vector of residuals. Then F receives a formula. A formula is what we use when we do a regression. It's usually the thing we have with the tilde. So this is just that first part when we were doing LM robust in the past. This is the first part we're typing, our independent variable, and then our, dependent variable, and then our independent variables and the rest of the regression. So I put some comment here, regression formula. Then here, J, from the first 1 leg until 10 legs, we're going to do the following. K is the matrix row. So this K here, where is it? Where was our matrix? BP test. It will be going from 1, 2, 3, 4, 5. And there is a little bit of a calculation going on, but pretty much it will be the first leg, it starts at 1. So 1 minus 1 is 0. So this part here disappears. Then we have the J, 1. And that's how it continues going. After, when we're moving to the next model, will be 2 minus 1 in the I, because I's are the models. 1, so 10 plus 1 will be line 11. So second model starts at line 11. You will see 0, 2. It's where the next one starts with J1. Okay. So, all right. This is just showing which row we're typing things. Second, it's a pretty smart way of doing the regression, because we will update the formula we have inside of F. So first, E2 underline I was regressing at 1. Now, for the first leg, we'll update it, and we will get whatever we have, and then we will add this part here. So we're adding, in the first run, we're adding lag 1 to it. So we will be regressing our residuals squared into the lag 1 of our residuals squared. Let me see what I had. So look at this. The first regression we're doing will be a regression of this guy on just this first one, just the first leg of our residuals squared. And then we will keep on doing, but adding the next one. So this next regression will be having a constant alpha 0. Then we have alpha 1 plus the first leg plus alpha 2 in the second leg, and it keeps on going until we get to our 10th one. Okay, that's what we're doing in there. All right, we did a regression. Now, let me show you, just to have an idea, what is the last one. After we did the 10 legs, this is how this F is going to look like. So the regression of errors squared on the first leg, so leg of itself n equals to 1, then leg of itself n equals to 2, so the second leg, then the third, fourth, fifth, sixth, and then goes until the 10th. And so this is a quite smart one. I think it's interesting to see how it's done. Starts with something relatively empty and then goes updating one by one, depending on which leg we are. Then next thing is to do the regression. So BP reg J is receiving an LM. It's not an LM robust, because we're not worried about the standard errors for this one. Let me see. No, we're not. We just want to extract the R squared of this regression. So this is what we're doing. LM is, BP regression for J legs is receiving this LM regression with the formula. So once again, for the last one, the formula will be this long guy here. For the first one, the formula will be just up to here, second one up to here, and there it goes. All right, this is what this guy is receiving. If I run it, it will show the coefficients. If I did a summary of it, it would look like that, as we have our regressions, right? Summary. These are the coefficients for each of the legs. That will be for the last one. Next one, we're calculating this Lagrange multipliers statistic test, or LM statistic test. And this is what we're doing here. Look at this little formula with our R squared of the errors. This is saying the following. We have the length of E2 underline I. The length is pretty much how many observations we have. E2I. As you can see, the length is 2604. I hope I'm not wrong. If I run this guy, 2604. Times the R squared of that regression that we just did. Look how we obtain it. We had the summary as I ran before. Now we're getting the R squared. And this is for the regression. This specifically, it's for the regression we did for the last one we did. So by calculating all of this, we're getting 142 for our test statistic. So here, test statistic, right? And this is distributed as a chi-squared distribution. And that's why we will be using the probability of a chi-squared in here. So look at that. Now, to get our p-value, we're getting 1 minus the chi-squared probability of getting this value, given I have these degrees of freedom. This is the number of legs. So it will be between 1 and 10, depending on where you are in your matrix. So what is the chance? As you can see, what is the chance of getting 142 out of 10 legs? I think that this J should be 10. It's pretty small. So if you run the last p-value we had, it's very close to 0. It's pretty much 0. Okay, that's the value you just calculated there. But of course, when we had different values before, while this 4 was running, it's a 4 nested inside of other 4s. So we had different values. And after we did all of this, BP test, so the matrix BP test, in that row K that we said, that we calculated here, we'll receive this adequate set ARMA, so PQ values. Then we'll receive J, that is here. Then we'll receive our LM statistic, and then we'll receive our p-value. And that's how we got our Bruce-Pagan tests there. Okay, a little bit, quite an in-depth explanation of the code. I don't think you would need to change anything for this code, unless maybe how many legs you're considering here. Probably I wouldn't do that unless you're something specifying that you have to change. Up to 10 legs for our Bruce-Pagan. And that's it for question 5. That's what we have to do to calculate. And what is going on with our results then? The null hypothesis of the Bruce-Pagan is that our model is homoscedastic. So all those alphas we talked about, all these alphas in here, 0, 1, 2, probably not the 0, 1, alpha 1, alpha 2, alpha 3, they are equals to 0, right? But since we are rejecting, because we're getting a p-value smaller than 0.05, we're actually getting very low p-values. We are taking we're rejecting in favor of the alternative hypothesis, which is there is heteroscedasticity in this data generating process. So we can say this suggests we should consider expanding our adequate set of models to include conditional heteroscedasticity. I hope that is making sense. So pretty much we've estimated the models, got the residuals. It looked like a white noise, but then some tests are indicating there might be some conditional heteroscedasticity or some conditional volatility changing, or have some volatility changing throughout time. So more in a certain period and less in a different period. It's not just random and it's not just constant. That's what's going on. So from there, we move to exercise 6. Expand the adequate set of models to specifications with heteroscedasticity. To this end, only consider conditional variances model with arch-gauge residuals. Hint, use rule-gauge package and U-gauge spec U-gauge fit functions. And just a hint saying what we're going to use. So let's go. Let me see if I click in here before. Oh, let's go to the code. Question 6. So we're going to start this new list of models called ARMA-gauge estimates. We started with this list. Thank you. Then another matrix, and now this other matrix will have 6 columns, of which they are P and Q again, but we're going to change it to PM and QM, which autoregressive legs and moving average legs, as we knew before. But now we also have a gauge PQ and a gauge. These are the gauge legs, P, and the arch legs, Q. Okay. And then we will have our information criterion, our Akaike information criterion, and Bayesian information criterion, AIC and BIC. These are the columns we have in our matrix. So what are we talking about? 3 to the power of 4. Let me just create this, guys. 3 to the power of 4 is actually going to run the code because it takes a little bit of time to run. So while I'm explaining, it's running in the background. 3 to the power of 4 is there because we are going to be given values for all these 4 legs from 0 to 2. So will be 4 fours, one nested inside of the other. And each of them will have 3 different values. So 3 times 3 times 3 times 3 is equals to 3 to the power of 4, which is equals to 81, right? So this is what we're doing. And then column names, we have, and then we create an I. This I is just the row indicator. So it just shows which row we're doing. As we did before, another way of doing this indicator, it's starting it as 0 and incrementing it every time you get to this point here. Or you could start it at 1 and move this line to the end of it in here, but the increment to say, okay, let's move to the next line. This is one way. The way we did before in here, it's a little bit more specific, but it calculates where you want to go every time you are doing it, right? Not too different. So, okay. We start at 0. There's no in R, there's no row number 0. So we start by incrementing it. I receives I plus 1. So now it's 1. We are getting the IC ARMA-gauge I. So the first ARMA-gauge model we have inside of this. Let me see. Oops. No. In the matrix IC ARMA-gauge that we created, we're getting the first model. Everything starts with 0, so it'll be 0, 0, 0, 0. We're putting it in the first 4 columns, so the first 4 values in the first row. Look here, first 4 values, 0, 0, 0, 0. Then, after that, there will be 2 parts of it. So first, if both our pH and QH are equals to 0, which means if we have 0 legs for gauge and 0 legs for arch, we won't be using U-gauge spec and U-gauge fit. We will use this alternative, which they recommend when you're not using any arch and gotch legs, it's better to use RFIMA spec and RFIMA fit. Okay, just a little bit of a side thing happening here. When both legs are equals to 0, we will use these ones. And when it's not equals to 0, then we use UGARCH spec and UGARCH fit. But let's go into details now of what we're doing here. First, we will generate a model. So we will run this RFIMA specification, and I can open here in the help. RFIMA specification, and we're given a value for min model. This min model receives a list of ARMA order, and this order will be our autoregressive legs and our moving average legs. For this one, we don't need to give an arch and gotch model values, because we already know if we only get inside of this part of the code if gotch and arch legs are equals to 0, right? So gotch, arch. After we generate a model, after we run this specification, then we run the RFIMA fit. So it's two-step thing, different than our ARIMA who did everything in a single step. This one is 2 steps. So RFIMA fit, where we use this model that we just created before, and we'll show you the data that we're working on, which is it's just our returns of the Commonwealth Bank stocks. All right, so we create this ARMA gotch. From the whole ARMA gotch, the only thing we're going to be saving, we will use this info criteria. This info criteria generates many information criteria, apparently, and we're just taking the AIC and BIC. Look, calculates and returns various information criteria. We're just taking the first 2 of them from 1 to 2, which will show us AIC and BIC. I'll give you an example here, but if we don't select that thing and run it like that, Akaiki, base, and then Shibata and Hanan Queen are all of the information criteria they generate, okay? This is how it saves. So when you look at your, where is it? I see ARMA gotch. Then we're saving the Akaiki and the BIC model. Those values are not for this one, are for the last one. Okay, so this and this, because we have run everything already. So first ones, it's for 0, 0. Then when it's not a 0, 0, then we have gotch and arch models. And the thing here, you'll see the same thing. There is a UGARCH spec, but the difference now, we have some heteroscedasticity legs, let's say, a gotch and arch legs. So we have to give them a min model, and we also given a variance model. So let me put the spec here. Univariate gotch specification. So we entering a variance model. And min model, where is it? Min model is here. Okay. So autoregressive legs, moving average legs, gotch legs, arch legs. So first we generate the model. It's kind of our ARIMA order, if you want to think about it. And then you use this ARIMA order type of thing. Now it's an ARMA gotch model to do the UGARCH fit. Univariate gotch fit class, which receives a model. So it has to come in the format we generate here. So the model, our data, once again, as we did before, and then the solver equals to hybrid. Let me see. Oh, where is it? Solver equals to hybrid. It's the strategy we're using to solve it. But that's it. We're going to run. And once again, we're just taking the AIC and BIC from this model we generated. And after doing all of that and going super in detail on what we're doing. We're going to get the top 40 AIC and the top 40 BIC. So top 40 out of our 81 models, right? If you look at this, guys, you will see a lot of things there. Then a lot of things for this one too. And then we're going to find the intersect of both. The intersect is still pretty large. Look at it, 39 models. IC int ARMA gauge. But there is one caveat here. We're not considering models, which ones, let me double check that. We're getting just from 1 to 36. Look at this, just up to here. So we're not considering models that are gauge without arch. Okay, we're not considering these guys here. So if you have some value in here, we expect to have some value in here too. In this case, it doesn't, so we're not going to consider these guys. Okay, so we're moving on with 36 models. This is pretty much how we did things before. So we get the top AIC, top BIC, then we get find intersection of AIC and BIC. And there are a lot of models that have comparable AIC, BIC measures. We selected for 36. And then we're going to manually check their autocorrelation of legs. It's a little bit how we did things before, but let's go, let me see. Yeah, so we're doing the Young box, but it's not well defined for heteroskedasticity because it assumes homoskedasticity. So we will have to do this to check the first 10 legs autocorrelation by hand. So let's go there. First, we check the number of models. Now it should be 36. Let's see here, and mods 5. No? Oops. Okay, I haven't run this lines. Let's run everything. And mods 36 now. Then we have SACF gauge. Now we're creating this matrix to store everything. Number of rows will be the number of models we have, and number of columns will be 14. And why is it 14? Look at the column names. We will have the autoregressive legs, the moving average legs, then we have the gauge legs and the arch legs. Okay, these are the first 4 columns. The next 10 is just the legs, the amount of legs. We're analyzing the autocorrelation. So if you think about the ACF, it's each of the bars that we have in terms of autocorrelations, but starting from 1. We're not doing leg 0 because leg 0, it's always 1. Okay, so let's go. I will run it. And then first, let's have a visual of how it should look like. I'll put in the screen here. This is how it's going to look like. So amount of autoregressive legs, amount of moving average legs, amount of gauge legs, amount of arch legs. You will see we didn't choose any with 0, 0, probably because there was pretty clear evidence that there was some heteroskedasticity, so they didn't score really well on AIC and BIC. And we also eliminate the ones that had gauge legs without arch legs. And then we have the 10 legs here, the autocorrelation for the first leg, second, third, fourth, and go on until the 10th. All right, let's go back. Let's show step by step what's going on. So for each of the models, which is our little I there, I is also indicated which row we're doing. First, we will take the legs. So we'll take information for these 4 things here. This comes from the adequate set of ARMA, or the first to 4th column. So adequate set ARMA gauge, You click there. We're just taking this first 4 ones. Then, to calculate those values we saw in here, 1, 2, 3, 4, 5, 6, until 10, we will do an ACF, and look what we're doing here. We're getting this ARMA gauge estimate. Inside of it, we're looking for the specific model, so adequate index ARMA gauge that we generated here. So the first one, adequate index ARMA gauge, you can come here, adequate index ARMA gauge. We're going to, the first one will be the number 5 in this list, in the ARMA gauge est list. So we get this guy, number 5. And then we take this fit and then the Z value. So let's see if we can find it inside. ARMA gauge est. Let's open it. I think I'll open it like that. We saw it's the 5th model. Then we chose fit. Can you see here this little fit? Now we're getting this Z there. Okay, this Z will be there. Then what we're doing, store ACF values like 1 to 4. This is the ACF formula. If we would print, this is going to return the values for us from 0 to 10 legs. This is the autocorrelation. This returns the autocorrelation of the legs. And we're just taking from 2 to 11. So we're taking this second one until 11, which is the number 10. We're not taking the 0 to our matrix. So this is a little bit what we're doing. If I had, for example, equals to true, as you know, this ACF looks like that. It's a pretty low thing. We just have the first one very large. The rest of them are very low. But okay, this is false, just to keep as it is. And pretty much what we're doing is doing it for each of our 36 models, which generates this very large SACF gauge table here that goes down to 36 and analyzes all the autocorrelation legs. So when you look, you see that all the values are very small, including everything in darker green is smaller than 0.05. You can have a look if you want to each of them. I put a slightly different color here for our, just because it's above 0.05, but this is still okay. Usually the ACF doesn't use a cutoff of 0.05. It tends to be considerably higher. So it's still okay to have these ones for the first leg in our first 4 models. So everything is, so in this case, let me move on. Oh no, everything is all right. You see here, autocorrelations appears to be relatively small for all models. And that's what we're getting. Finally, let's go to 7. Estimate each model in the set identified in question 6. So we already have estimated these models and plot the estimated volatilities. So HT hat, interpret the results. Look what we're going to have. It's pretty simple now, since we have everything stored in ARMA gauge estimate. We're only going to plot this estimated volatilities. So we'll have estimated all the models. You will see, unfortunately, RuGauge package does not provide standard errors or confidence intervals for the estimated volatilities. But we will go on. This is just an F going for each of them through each of the models. I will delete this one because I delete this. This is, the rest is all right. Just going through each of the models. The first one will be just, let me run. We'll be just generating the title, you will see. And this is what is getting ARMA, both of the coefficients, then a little dash, gotch, and both of the gotch arch coefficients, right? And we're doing it for all the 36 models. So generate the name and doing a plot with date -1 as we did before. And then we're going to generate, use this estimate, the model. Once again, we get the fit there. So we're getting this number of the model. Once again, the first one, adequate index armor gauge. First one, adequate index. Where are you? Did I not save you? Oh no, it's down here. Adequate index gauge. First one will be 5, then 6 and 8. Let's look at the second one, 6. We will go there and get fit and then var. So arch gauge. Let's close 5, 6. Fit, and then we're getting var, the variance. This will be the estimated variance that we are getting, and then we're plotting it as a line, and no labels for the x, but in the y we call it volatilities, and then we have the title there, my gauge and the model. There are 36 of them, and you will see that they change a little bit. You'll see a little bit of movement, particularly in the larger volatilities. Have a look while I'm clicking through it. So these two are relatively different. Look. But they still look pretty much the same as you go through the list. Oh. They change a little bit, but they map quite the same thing. But let me go to the beginning and compare it to the errors squared that we had before. Let me see if I'm going through all the 36. Oops, there we go. So these are the errors squared. 20. Let me delete this guy. Look, it is mapping relatively well, whatever's going on there. So you can see we probably, although we have a lot of uncertainty with the models, there were like 36 models, they are all resulting something very similar, which is a good thing. It seems like our specifications are quite robust with what we're trying with modeling the volatility for this data set. And for this tutorial, that is it. So today we did use R to infer the presence of heteroscedasticity during the Bruce-Pagan test. We first saw some things in the autocorrelations in the ACF of the squared residuals, and then we did a formal Bruce-Pagan test and confirmed. Then we constructed an adequate set of models with possible gauge errors. So we use RuGauge function library with the model and fit, the specification spec and fit functions, and constructed it. And then we used R to estimate the volatilities based on the models with gauge errors. All right. So thank you so much for watching another tutorial. And if you have any questions, feel free to jump in to our consultations. And good luck with your report. See you next week.